Okay, bom dia, good morning. So let's prepare ourselves for that. The von Neumann stability analysis, which is basically, to some extent, we'll see Fourier analysis, and we're going to end up seeing an amplification factor. It's going to look a little bit, that's not the same, of course, as things we saw for ODs. So my notes sort of go between things of strict vedada, and also there were some notes at one point that Trefethen had on the web. I haven't checked if he still has it, but it's not his spectral methods book, which were quite good. It was like a sketch of a book. So I'm getting things here and there too, and also sometimes a little bit from also Levesque's book, which is an OD book. Levesque has three very good books on numerical sort of differential equations. One, we have the three of them in the library. One is a blue cover one, which is like ODEs and that I forgot exactly the title. There's a green one, which is, the title has conservation laws, it's more specific to conservation laws. And there's a red one, a thicker one, which is finite volume. So all these books, there's parts which are very good. So it depends a little bit on the topic. But the books are very good. Okay, so I'm getting, I think, starting with things from Trefethen and going to strict vedada. So pay attention, I want to say this before I forget. Okay, so pay attention in the things I will write now, start writing today, and in the notes. I almost got confused with myself reading my notes that I wrote some time ago. But it's because the notation is the following. So I'll call your attention, but I want to mention before I start. Many authors, right, use, as I told you, I hope someday I rewrite this, this text in a more uniform notation, because I was using from here and there, and it's actually nobody's fault. Okay? So some authors use K and H for what? Have you seen that? You know what I'm talking about? Some authors use K and H as the discretization parameters. Okay? So notice some books that say K and H, where H is delta X and K is delta T. Right? I think strict vedada uses that. Some authors. And I think the reason is basically you have to type one letter instead of typing Greek letters for delta X, delta T. It takes less space. Okay? Then some authors use K. Like me, I like using K for wave number when we go to Fourier, right? Some authors then use, sometimes because they use K for delta T, they use Xi, this, right, the Greek letter Xi, for Fourier modes, okay? Because some of you already saw my courses, since I use in some of my problems complex variables, I might mention complex variables numerically at the end of this course, but I like using Xi for the real part of the mapping, right? So there's this dance of notation, excuse me, but here Xi will not appear, at least for now. And in the notes, I'll be appearing K as delta T. And then when we get into von Neumann, you know, I'm going to write some things. I already used K sometimes for delta T, and then it will become wave number. Okay? So pay attention to that. I think from the context, it's going to be clear. If not, ask, and I apologize a little for the notation dancing a little bit around. Okay? All right, I had, I think, something else to say. Well, it escaped me if it comes back. So there are two lemmas. So in Trefethen's notes, there are two lemmas, sort of, to some extent, elementary lemmas. And let me write them and indicate the proof. It's very simple. So the first one, things that are useful. So let, okay, this one is very simple. Okay, so this one is very simple, right? Just, take the exponent 1 over b on both sides and so on. And this will be used then in lemma 2, that first part. And lemma 2, I will write it in the way it looks like, just a simple lemma, right? But I'll write it and I'll speak, after I write it, I'll speak with the sort of the discrete operator point of view. So let me translate here. It's written in Portuguese. Let me translate in English. So let SQ be a set of non-negative numbers indexed by k, of course, no big deal, right? Needless to say, with capital T greater than 0 constant, right? A fixed constant. Then, sorry, I got to translate this in real time. SK, okay, uniformly for all k and n, kn less than capital T, if and only if Sk smaller than order k, Sk goes to 0. Okay? So this just looks like playing with numbers, right? So you have a set of positive, non-negative numbers, Sk. So let me put some notes to you so that we can put this into context of our course. Okay? So we should think, one way of think of k, as I mentioned, delta t. So delta t small going to 0. Okay? And we can think as Sk as norms of operators. Because this is going to be used, somehow this is in the context of stability. Okay? So this has nothing to do yet with discrete differential equations. Let's put it this way, right? Difference of it has nothing to do. But as I already showed you, well, I think I'm showing you more in detail today, we will allow in some cases the number, which has to do with the norm of the operator, I think I already showed this to you a few classes ago, to be slightly greater than 1. And this is actually going to be a little bit that constant Ct from the stability definition. The constant Ct, so T is basically, right, this is not an index, this is n times k. Basically, T or k indicates our time interval. Okay, so basically, look, this is the step n delta t, right? And we're looking for n's and delta t's such it is in some time interval. And somehow, in our stability definition, we had that constant c of t, right? That actually could be exponential, but we would control the stability of solutions. So this is where this is going to be useful, okay? So let me indicate the proof of this. So this thing is that it's if and only if, which means this. If we have this, right, we get this, which is the control of the operator as we're evolving in time, to some extent, right? And if we have this, it's because basically we can find a constant so that this is controlled by 1 plus a constant times the delta, the time step, okay? So it has to do with stability. Go back with the notes and you'll see. Look at this at your own time. Okay, so basically the proof, okay, let me indicate, right? I'm going to not do every detail. It's here in the notes. The notes are written a little messy, but, you know, good exercise for you to clean it up. So in this direction, which means this guy implying that guy, okay, so if we have this, one plus order k, then this means this, okay, and the rest sort of follows from lemma 1. So check that, okay? Then this direction, if C is C1 is less or equal to 1, then it's easy. Okay, check that. So I'm going to sketch now for C greater than 1. If C1 is greater than 1, and, right, we have this SK smaller than 1, this guy here, okay, then I basically can do this, right? Put this guy here. This is equal to 2 over T. Let me get this right. I didn't do anything. Okay. And if we look, say, at the second half of the time interval, so for n, so if this is uniform for nk greater than t over 2, which is the second half of time interval, right, we get this is 2t over k, okay, and then this will lead that we can find a constant for that this is smaller than this for when k going to 0. That means k small. I have some sketches here, so check that. If it's not clear, check that at your own time. Okay? So recall these guys are positive, greater than 1, and so and so. You can get this. Okay? So check the details. So basically, right, we use the second half of the interval to write that, to write in a form that basically we have. Look, note that this is basically, sorry, my handwriting is bad. So this is just basically some value, say a to the k, okay? And then you can get this. All right, so let's keep on going. So I'm using now, so consider, so this is the part that Trefethen in his web notes has this, I thought it was well explained. Consider the evolution equation, and he writes it like this. Okay, where we're in the time interval, just as mentioned. U0 is equal to U0, and A is some linear operator in some Banach space. He calls it B, from B to B. Okay? So write complete space with a norm. Okay, let's put it with a norm, with, say, the norm. He just indicates like this. Okay. So Trefethen's mentions this. This could be sort of a PDE. Okay, he mentioned that, or already method of lines, which means that the spatial part has been discretized, and for example, this could be a matrix. Okay. So, so let me mention here as a note. We can think at this stage that we have the method of lines, or some operator A. So the method of lines, this would be a matrix. Okay. So having this in mind, then he goes to the following. And then you see the connection with what was said above. So he writes this. Okay. So this would be our notation for a discrete operator, right, that sort of evolves our method, okay, our solution. Okay, and we can do this in such a way that sort of, let me see how I should say it. No, I don't need to. So, you know, we could iterate this and so on. So here there's already a little bit of a notation problem. For the time being, I'm keeping a list, or a notation, not a problem, but awareness is that I'm using this notation here for an operator, right? This is like numerical method, right? Gets the solution at one time step, poof. Operator gives me in the next time step. So the problem of the notation, or the awareness of notation from here to this one, is that this is a set of non-negative numbers, right? And over there I'm writing it as a discrete operator, right? So beware of the context. So this S here could be actually the norm of this guy for a given time stepping discretization, okay? Right? So sometimes, at least in the class, if I remember to say everything, but sometimes I don't remember to say everything, so then that's my problem, not your problem, then you ask. But if I remember to say everything, you know, as we get mature in a subject, sometimes the notation being a little loose is not too much of a problem, because it's an exercise of understanding the context and saying, oh, this is an operator. Oh, this is a number, okay? But I still prefer unambiguous notation. So that's why I was making my first comment at the beginning of the class anyway, right? Okay. So this, if we have this operator, okay, this is the notation for an operator. And then let me actually write it. Then we see in Trefethen's notes, as I recall, something written like this, which this just means going backward, right? An iteration of the operator. And then he gives the following example. Let me maybe put this here so I can use the blackboard. And then we have the following. So let me write like this. Let's see if I can translate in real time. Consider the scheme or let me maybe say the one-step scheme, one step in time. Okay, so he writes this abstract scheme like this. So I don't know why I wrote here. This is R. So this scheme has a molecule like this. Right, at first. This scheme has a molecule like this. So it's a one-step method because this is n. This is n plus 1. Right? J is basically our reference node. And the method is explicit if the beta, say, 0 is different from 0, but beta j, or beta nu, sorry, is 0 for nu different from 0. Right? Because beta nu 0 would be this guy here, only this guy, right, using at the next time step. But why this is written like this? Because this actually method can be written in matrix form. Okay, this is the method written matrix form, where, let me go this way, where A and B are topeless matrices. That is, matrices which are constant along the diagonal. Okay? So note that we are not, right, topeless matrices like this. Constant along the diagonal, maybe might have zeros here. Okay? Just remember that if we set this, I'm not taking care of boundary conditions. If I say, oh, we have periodic boundary conditions, then these matrices become circulant matrix, right? The matrix that sort of the coefficient sort of comes back in the other side because of periodic boundary conditions. Let's not worry for this at the time being. And the things that this is going to lead us, let me skip, I think, some parts here where I think I'm repeating things. Right? Yeah, I'm repeating things of the operator norm. So, when we have this kind of structure, Okay? With topless matrices, namely, we can write the above method as discrete convolutions because of this, right, sliding sort of invariance. Oops, no, and. Okay, where, let me put this here, where the entries would be this. Okay, I hope I have this right. I haven't checked it, but basically, right, the matrix is as we cut it here, right? It's like something. The coefficients are sliding, so it's like a discrete convolution, and therefore, this allows us to do the following. So, using Fourier, we can rewrite this as b hat n minus 1 a hat b hat a. Now let me put the k's in, sorry. Right? We're now, so call attention, now I've changed the notation. So we have this, right? Because we have this discrete convolution, right? If you don't remember this, even on Wikipedia, if you put Wikipedia, for example, you refresh your memory, you see, right, the connection with Toplick's matrix and discrete convolutions. And if B, so if BK is different from 0, for our case, all the k's in this case, so here we should put K is in our interval. Oops. So this is also, so now K is not delta X, right? And from here, we get the amplification factor. Okay, so this is then our amplification factor. Let's see if I wrote this right. Yeah. So you see, because basically when we do the Fourier, the Fourier, in particular in space, right, not only things decouple the modes, it's linear. So we got something a little bit like a structure that would be something like an ODE, right? So if we have a method that's like this, right, a method that's like this, with this structure, we identify it as a convolution because of Toplick's matrices. Therefore, we go to Fourier space, right? So if we go to Fourier space for the spatial part, our system looks like an ODE. And again, we're back to something that looks like an amplification factor, which takes us from the previous step to the next one, but now Fourier amplitudes, Fourier modes, right? This is the amplitude of the Fourier modes, and that's what, if we do the Fourier analysis of the simple wave equation, right? What we get is an ODE for the oscillations in time, which means if we did the Fourier analysis in space, we already set how we are understanding the oscillations in space, which is e to the I k x, right? So, but here we're thinking about e to the I k delta x, blah, blah, blah. Okay? So this is our amplification factor, okay? And, and basically, one can then write the following. If G, K is continuous in this bounded set, right, which is where, let me repeat it here for, then we can write the, for example, right, the infinity norm of G, which is the max in that interval. Well, let me repeat it just to be on the, so we have the maximum value of our amplification factor. And we basically can then say the following. If I have the norm of this, well, this is the same as this, right? Because in Fourier, right, this is what we're doing, and this is less or equal to this. Okay, and since we saw the discrete Parseval, we can then write this, okay, which then shows us what? That basically, right, dividing this by this and so, we have this, then the amplification factor, one way of showing that our discrete operator is bounded. Okay, a bounded operator. Okay, so this is how we relate all these things. And then, therefore, we can write then the von Neumann linear stability condition for a single-step method, a single-step constant coefficient method. No, sorry. The von Neumann I'm translating from Portuguese and English sometimes, so I'm getting there. The von Neumann condition, the von Neumann linear stability condition for linear constant sets that stability of that the method is stable in little L2 delta x, right? If and only if the amplification factor, excuse me, satisfies this condition as delta t goes to 0 for all k of our grid. Okay? So basically, right, that was the condition we saw, I think, last class, that this could give us, for example, an exponential, but an exponential that depends on the constant Ct, which is related to the constant Ct, right? And that is independent of the discretization. Okay. So let's see here, over here, one example. I mean, if we do the Fourier analysis of a method. Okay, so this is the way the von Neumann condition, right, does through Fourier sets a framework that looks, definitions of stability, which is the solution is bounded by some constant that is fixed for a time interval, but could grow exponentially as we increase the time interval. So it depends on the capital T, right? This same kind of object that appeared even in our proof of the convergence for the explicit Euler. So we see these guys coming up over and over. Okay. Yeah, so this is one example. So we take this an example. I take this equation. And let's take this molecule, which means we have, so this is, I think, an example now from Strickwerder. Yeah, I think it is, yeah. So do you see, is everything okay up to here? Do you see anything wrong? Or is everything okay? Everything's okay, right? I mean, maybe the first thing I would think you would react, oops, is this molecule? The molecule is good to indicate quickly what this guy is doing, right? The molecule here looks like a downwind, right? But that's okay, because the equation is propagating to the left. So just a little, maybe just a little, I don't know, streak further, maybe did this example a little bit, just whoop, just pay attention, everything is fine, right? It's basically in the right direction. So now we've seen how to analyze, one way which is very interesting to analyze numerical methods for this equation, for example, as I did, I like it very much, is the modified equation, right? You write it playing with Fourier, with the Taylor, not the Fourier, the Taylor expansions, and you get the apparent, the numerical, diffusion if the method is diffusive, which is this case. Now we're going to do this stability analysis in a slightly different way. We're going to do a Fourier analysis. Okay, the Fourier analysis of the method means that I'm going to use Vjn as a Fourier mode, generic Fourier mode. Well, what is a generic Fourier mode? It's this. Okay? This is my discrete Fourier mode. Okay. And I think it's something you probably already know, in particular doing some of the problems, that these kind of modes, not only I'm doing here an analysis of, we did the analysis of the equation which we call the dispersion relation, right? I think at this point in the book, he's not even calling it dispersion relation, but and in particular because I did not put a Fourier mode also for the temporal part, right? I already did dispersion relations quickly with you here, right? Something I do in more detail when I do PDEs or fluids, but you remember this, right? We checked for the wave equation. Do you remember what I'm talking about, right? Which is, from your expressions, maybe not, and maybe I am wrong, but let's see. Say if I have this wave equation, and I just put a Fourier mode like this, and I substitute in here, right? Did I maybe not do this in this class? Maybe not. From your expressions, I've seen it, maybe not. Let me do it here quickly. So if I do this here, right, look, I have oscillation in space, oscillation in time, but it's just basically a Fourier mode. If I plug this into here, right, we did this, at least something similar for the interface stability problem. So we get the dispersion relation, which is omega of k is equal to k. Check it, right? So the PDE becomes an algebraic relation, which is called the dispersion relation. And we can do that for the numerical method too, right? So if you do this for the, so this is a good exercise. If you do this for the upwind, or here it's the downwind, but it doesn't matter because the wind is blowing the other way, right? If you do this there, you're going to get the dispersion relation, and it's not going to be exactly this because of the operator approximation. And therefore, that's one way of seeing that the method is diffusive or that the method is dispersive. We saw that upwind was diffusive, and for example, Lax-Wendroff is dispersive by looking at the modified equation and looking at the new term, higher order term that appeared in the operator, right, in the modified equation. For the upwind, it was basically a UXX term, so it was a diffusion term. Okay, so it would be here a diffusion term if you look at the dispersion relation for the diffusion equation, for the heat equation, do this for the heat equation, right? Do this for the heat equation. This is the wave equation, and you see you're going to get an imaginary part here that gives you the damping of the mode. Simple exercise. If you have never done it, do it. Okay. Now, if I plug this guy in to here, okay, if I plug this guy into here, where x is this, kxj, the discrete x, and time is the discrete time, is n delta t, I will get the discrete dispersion relation, okay? Which is an interesting way to see numerical diffusion or numerical dispersion, okay? So in this case, actually, since this is equal to that, look at this. I put the k here. I put the k here. This is a constant. It's equal to 1. And we see that all Fourier modes travel with the same speed. So therefore, that's why this equation is not dispersive. It's a hyperbolic equation. All the modes have the same speed, right? Remember, I mentioned this in the course beginning at some point. Now here, we're doing something a little different. Nothing deep, is that I'm only discretizing in space, right? So basically, I'm only discretizing in space, and I'm going, instead of looking at, I could go to the ODE and then do the Fourier analysis of the ODE. That's what we're doing by seeing how this guy behaves, okay? But also, okay, in discrete time. Okay, so here it's discrete. It's like doing discrete time. So what we get the following. So let me skip one line of the calculation, because this is getting terms and canceling terms. We got this. Okay, so basically, plug this into here, okay? Clean up some terms, right? It's in the notes, 2 steps in the notes I'm skipping, but it's simple algebra. Plug this into here, clean up some terms, which are some of the exponentials, and we arrive to, excuse me, to this, okay? So look, this is like our amplification factor for the OD, right? So I could have just plugged this in, say to here for the spatial discretization. We would have the OD, but the OD has been discrete too, so we get this, okay? So let me go back and just fix something that I didn't say, is that the numerical dispersion relation is when you sort of propose that you're going to have also a Fourier mode in time. And then you get the relation between omega and k. Here, in this ansatz, I just let this guy loose, right? I didn't predefine its form, but so therefore it comes out like this. Okay, so there's no omega. So this is the amplification factor, okay, which we can then graphically see it like this. So let me put a point here. Okay, so look, if you write this 1 minus sigma, and then rho e to the I theta, right? You're like in the complex plane in this thing. So basically J of k, let me write as in the notes. K delta x. And so therefore, right, belongs to this. And we see that if we want, for the wave equation, we want this guy to be less than 1, right? Because there's no growth, then this sets values for sigma. So this means sigma less or equal to 1. The way to interpret geometrically this guy over here, okay? But recall, in some problems to have stability, right, we can allow the sometimes being slightly bigger than 1. Okay, so let me see, time is... So there's some times some exercises you can do of this kind with other methods. Yeah, today I have to maybe finish earlier because I have some meeting on the internet. Let me see here. Yeah, I think because I have a meeting in the internet, I think I'm going to finish today here. Okay, come back on this next on our subject next class, and today the lecture will be shorter since I have to do something, and the assignment is what for this week, right? No, what was the date I gave you? I forgot.
Next Monday.
Next Monday. Okay, lucky you. So I was thinking this Thursday. So you got extra time. Not truly, right? You got the right. So good. Okay? All right, so let me finish here today, and we'll continue on Thursday.